So our next presenter is Myriam Prasso-Aymon. She is a new master's student at l'Université de Montréal in Quebec. She's supervised by Julie Flavachek-Larondo. Today, she's going to be presenting a paper that she actually completed as an undergraduate research student in Professor Flavachek-Larondo's lab. Just quick disclaimer, I was on this paper with Myriam, and I think she's an absolutely fantastic student, so I hope you really enjoy this presentation. But what she's going to describe today is a detailed multi-wavelength study of a truly exceptional and massive galaxy cluster. And like I mentioned, this was work that she did as an undergrad, and it recently culminated in an accepted paper into the Astronomical Journal. So Myriam, if you would like to start, we're all listening. You are muted though.
Okay, perfect. Thank you, Carter, for the fantastic introduction. So I'm really happy for the invitation. It's actually my first talk, so wish me luck. So yeah, as Carter said, I'm Myriam Prasso-Aymon and a new master's student at the Université de Montréal under the supervision of Julie Flavachek-Larondo. And today I will present you a multi-wavelength study of the massive galaxy cluster MACS J1447. So just a bit of structure. I will start with a bit of scientific context. Then why MACS J1447? Because, you know, there's plenty of objects in the sky, so why choose this one in particular? And I will talk about the observation of MACS J1447 we got after the X-rays analysis, the radio analysis, the optical analysis, and finally some conclusion. So I'm not sure about your background, so I'll just start from the basics. So clusters of galaxies are the largest gravitationally bound structure in the universe, and they are mainly composed of dark matter. So around 85% of the cluster is dark matter, so we don't know what it is. About 3% are the galaxies and the stars, and the other percent is just gas. So here's a really nice image of a cluster of galaxies. Those are really interesting objects, and you'll know why after this presentation. So normally we separate the clusters in two categories. So we have Kuiper cluster and non-Kuiper cluster. So Kuiper cluster are cluster where the X-ray brightness peaks really steeply toward the center. So as you can see here, at the center we have a really bright peak, and it's normally really, really cold. That's why we call them Kuiper cluster. And here we have non-Kuiper cluster who are normally really more uniform. So what is really interesting with Kuiper cluster is that the gas between the galaxy, that's what we call the intra-cluster medium, we can detect them at X-rays via thermal emission. It is expected to really, really cool rapidly. And as you know, the star formation rate is really good when it's cold. So we should therefore really observe a really huge star formation rate. So about 100 to 1,000 solar masses per year. Just to give you an idea, in our galaxy, so the Milky Way, the star formation rate is about 1 solar mass, which is considered huge. So 100 to 1,000 is really, really more huge. However, that we don't observe the star formation rate expected. It is indeed really far lower than expected. So the question we're asking ourselves is, okay, there is some physical processes that is reading the intra-cluster medium. To this day, the most accepted theory is the active galactic nucleus feedback, which we will call AGN feedback. Just for the non-initiated, active galactic nucleus is a supermassive black hole and its environment. So just to resume you a bit, the AGN feedback processes is that, okay, in a cluster of galaxies, there are maybe thousands of galaxies, and there's always one galaxy who is brighter and more powerful than the other, so it really outstands from the other galaxy. And that's what we call the brightest cluster galaxy. I know, really original name. And the supermassive black hole. supermassive black hole in this cluster's brightest galaxy, it produces relativistic jetted outflows that we can see at radio wavelength. So here's a nice image of a relativistic jetted outflow from Cygnus A. So just to give you a bit of context, even if the supermassive black hole is really, really smaller than the entire cluster, it produces jets that have an influence on the entire cluster. So even if it's small, it has a super big influence. So with the power, what's happening is that those jetted outflow will inflate cavities. We also call them bubbles in the intracluster medium, and those bubbles will reheat the intracluster medium. So those cavities, we can see them using X-ray emission. So here's a nice example of the Perseus cluster. So in blue, you have the X-rays. In red, you have the radio. The faint peak here is H alpha, and the background is visible. So HIST, I think. As you can see here, we can clearly see those cavities, those X-ray cavities. Perseus is a really close cluster, so we can see them clearly, but for more, with a cluster with a more huge redshift, it's difficult. It's more difficult, but you'll see we have evidence of a cluster. So that was for the context. And now, why MACS J1447? So MACS J1447 is a massive Cougar cluster with a redshift of 0.3755. And this is, to this day, is one of the most massive we ever found. So we can better understand these AGN processes by targeting one of the most massive and strongest Cougar cluster known. So in really massive Cougar cluster, the AGN feedback must be operating at some extreme level to reheat the intracluster medium. Also, MACS J1447 is one of the most X-ray luminous cluster known in the literature. So here is a graph with the X-ray luminosity of many clusters. As you can see, MACS J1447 is the yellow star and is close to the Phoenix cluster, which is the most massive Cougar cluster ever known to this day. So now the observation of MACS J1447 we got. So we have 3 wavelengths, so X-ray, radio, and visible. So first we have X-rays from the Chandra X-ray Observatory. And we had about 20 hours of new observation in V-faint mode. And we already had 5.5 hours of past observation. Since we are conducting a multi-wavelength study, I will just enumerate the structure in our cluster that we can see at this wavelength. So we can see the intracluster medium, we can see the cavities, the active galactic nucleus, as well as the plum-like structure. The plum-like structure, I'll explain in more details in a few slides. Next, we have visible data from the Hubble Space Telescope. So we had observation with 2 filters, so F606, which is green, and F814, which is red and blue. And in visible, we can see the brightest cluster galaxy and the optical filament. Again, those structure will be explained in more details later. Finally, we have radio data from the Jansky Very Large Array. So we have 3 hours for both, for 3 configurations, so A, B, and C, at 1.4 gigahertz. At radio wavelength, we can see the relativistic jetted outflow, as well as the mini halo. So with all this data, it was possible to conduct a very powerful multi-wavelength study. So yeah, well, I'll start with the X-ray analysis of our cluster. So as you can see here, this is an X-ray image of the cluster, and compared to the Perseus cluster I show you in the slides, we cannot see clearly the cavities. So this is a really interesting fact about MACS J1447 is that we just don't see anything. So, but since they are jets, they must have cavities. So we did some subtraction. So we used some techniques to see the cavities. So we did an unsharp mask as well as a double beta subtracted. So the unsharp mask is this image. So we took an image really smoothed, and we subtracted from a less smoothed image. And now we can clearly see one northern X-ray cavity, one southern X-ray cavity, and two potential ghost cavities. So the potential ghost cavities are X-ray cavities that's been dragged out of the AGN radii. So see it as past X-ray cavities. So since we want to see, okay, is there enough power, is there enough energy to preheat the intracluster medium? So we therefore calculated the power of the cavity using the buoyancy time, and we obtained about 6 to the 10 to the 44 x per second. So we'll come back to these facts in the next slide. But before, I want to talk about those two panels. So here we have the same image, so the Chandra, but just separating the soft and the hard X-rays. So the range of energy are indicated right here. So in the soft X-ray, we can see a plum-like structure. So the plum-like structure could be created by the instability caused by the cavity and the gas excited by the intracluster medium gas. So it is not super well understand this structure, but it's still really interesting. And we see it at soft X-rays because we detect it from thermal emission, which emits principally in soft X-rays. Here we have the hard X-ray image of the cluster, and we can see a bright white dot here is the AGN. We can see in hard X-rays because the emission from the AGN comes from the Compton scattering, which emits hard X-rays. Okay, so now let's come back to the power of the cavity. As I said, the question is there enough energy to preheat the intracluster medium? So to find this, we calculate the cooling time profile. So the cooling time is the time that takes the gas, so just a bunch of gas, to completely cool down. And using the time at 7.7 gigayears, we computed the cooling luminosity. So here we have the cooling time profile for MACS J1447, but we also have the cooling time profile for Phoenix. As I said, Phoenix is the most massive Cooper cluster known to this day. We also have the South Pole Telescope average, and in the background we have the ACCEPT survey. So as you can see, MACS J1447 has a profile really close to Phoenix, which again makes the object really interesting. So yes, taking the radius at 7.7 gigayear, we calculated the cooling luminosity, and we obtained about 6 to the 10 to the 45 ergs per second. And since the cooling luminosity and the power of cavity are similar, we can conclude that there is indeed enough energy to offset the cooling. But you might say, okay, but there's an order of magnitude of difference. I know it might sound weird, but looking at this graph, which is the power of cavities and the cooling luminosity for many clusters, you can see that, again, here is the yellow star is MACS J1447. First, it's part of the scattering. And as you can see, MACS J1447 is just a bit lower. So what it means that even if MACS J1447 has powerful components, it just might currently be going through a phase of lower activity. So it's, you know, AGN feedback is a cycle. So it just might just be less powerful to this day. However, the offset between the luminosity and the power of the cavity is not enough big to conclude that there's not enough energy to offset the cooling. So that's for the X-ray analysis. Now I'll talk about the radio analysis of the cluster. So first we have, here we have the configuration A data. So the background is the X-ray image and the white contours is the configuration data from GVLA. And you can see here two structures about 32 kiloparsecond size, and those are the relativistic jetted outflow. So using this formula, we obtain a power of 20 to the 10 to the 24 watts per hertz for the jets. To continue, we have here the configuration C of our object, and here you can see a diffuse radio structure. That's what we call a radio mini halo. Radio mini halo are really interesting because the radiative lifetime of the relativistic particle is too short to spread over the radius that we observe for the mini halo. So there must be something reaccelerating the particles, which make the object really interesting. It is not my expertise, so I encourage you to see this paper from Annabelle Charles-Laferrière, who conduct a really detailed analysis about the mini halo in MACS J1447, but she also did a literature review about the AGN feedback, the link between the AGN feedback and the mini halo. So here's the archive link. And but we calculated the power of the mini halo, and we obtained 10 to the 24 watts per hertz. And again, this makes the mini halo in MACS J1447 one of the most powerful ever discovered. So not to go change MACS J1447 as powerful component. I just want to say too that both of those structures, so the jetted outflow as well as the mini halo, are both produced by the synchrotron emission. So synchrotron emission, we have relativistic particle in magnetic field, and it emits a photon that we can see at radio wavelength. Finally, we have the optical analysis of our cluster. So here we have the Hubble Space Telescope image. Here is the brightest cluster galaxy. And as you can see, there are two prominent filaments that they are 25 kiloparsecond size, and they are west-south and west-north oriented. And filaments are interesting because they are thought to be created from thermally unstable intracluster medium gas that would originate from the pushing back motion created by the formation of X-ray cavities. It might seem a bit theoretical for the moment, but I'll show you in the next slide, I'll show you a picture. It will make more sense in your head. So here we have the multi-wavelength analysis of our cluster. So radio, X-ray, and visible data all combined. So here in this image, we have in green, we have the direction of the relativistic outflow that, again, we can see at radio wavelength. In red, we have the direction of the prominent filaments that we can see invisible. Here we have the X-ray cavities in white and potential ghost cavities in yellow. So as you can see here, the direction of this relativistic outflow and the X-ray cavity, northern X-ray cavity, are perfectly aligned. So that makes perfectly sense. But here in the southern X-ray cavities, you can see a little bit of offset between the cavity and the direction of the jet. So this is one of many evidence that there are sloshing motion in MACS J1447. So sloshing motion is just like the intracluster medium could move depending on the physical phenomena that occur in our cluster. Also, you can see that the prominent filaments are perfectly aligned with the potential ghost cavities. So again, this is another evidence that filaments could have been created in the wake of the cavity. And I forgot to mention, in this image, the blue here is the X-ray image, and the background is the visible image. So what I want you to take home with you. So first, MACS J1447 is one of the most massive and powerful Coulter cluster ever discovered. Also, we found that there is AGN feedback processes in MACS J1447 since the cooling luminosity is comparable to the power of the cavity, even if there's a bit of offset between those values. Also, MACS J1447 has powerful and interesting structures such as the plum-like structure, the radio mean yellow, as well as the optical filaments. And the main conclusion of this paper is that the AGN feedback is indeed present in the strongest Coulter cluster known, around a redshift of 0.3, and may still provide a viable solution to the cooling flow problem. So thank you for listening to this talk. Here are my contact info, as well as the archive link to the paper. And just for this little spoiler, I'll just talk a bit I will talk about my master work that I will conduct in the next 2 years. So we will present the first high contrast images of X-ray binaries. So using Keck and NIRC2 data, we'll conduct a statistical study of the presence of companions such as Jupiter, brown dwarf, exoplanets in those extreme systems. And I want to thank all my collaborators that made this work happen, and I'm happy to take some questions. Thank you a lot for listening.
Thank you very much for that, Miriam. Yes, so we have plenty of time for questions, about 8 minutes. If anybody has them, you can either, you got some options. You can either ask your question in the group chat, raise your hand, or since nobody's talking right now other than myself, you can just start talking. Okay, Lawrence, if you want to post your question.
So I think you should declare success on your very first talk. That was a wonderful talk. Very interesting. It's a shame that you're going to stop working on clusters because you're doing beautiful work there. I think the ghost cavities are fascinating because there's no obvious source for them. They're not symmetric, so it's not clear that they came from where they could have come from. If you invoke them as buoyant bubbles, it could have dragged out the filaments. That could be, but the question is, why aren't they there on the other side? So there's some evidence in the Perseus cluster for offset bubbles as well. So I have nothing profound to say other than those are going to be extremely interesting parts of the story about feedback because they're there, but we don't see the radio galaxy, but they've got to be part of the heating scenario that went on in the cluster. So great work.
Thank you a lot.
Thank you very much, Lawrence. Do we have any other questions? We still have some time.
I just wanted to jump in with a comment, if you don't mind.
Yes, please.
It's Arif. Excellent talk. Really enjoyed it. I enjoyed both talks. In fact, I have lots of questions, which I'll probably send by email. What I did want to comment was about the offset cavities, the ghost cavities. There are two ideas that have been sloshing around, if you don't mind the pun. One is that there is large-scale motion in the ICM that are moving the cavities around. We did some work with that, and Marcus Bruggen has done some work with that, and it looks like you need to have had a very recent major merger to generate the velocities to do that. The other proposal that we put out, Chris Reynolds, Pratik Sharma, and myself, I think it was in 2013, that periodically the radio, the AGN itself will change direction, and that will then lead to a set of cavities being created in a completely different direction. Whether you see the back cavity or not depends on the orientation of the cavities themselves. If you look at Virgo cluster, there are a series of observations from radio through X-ray that actually show cavities being displaced, and some of the cavities and even the present day counterjet is not seen just because it's on the other side. So orientation is important. Is it black holes periodically shifting direction? Is it large scale motions in the ICM? These are interesting puzzles, and I'm looking forward to seeing the next generation basically try and resolve this problem.
I agree with you.
Yes, thank you very much, Ruth. And I'll mention this since Miriam did not. There is a further discussion on the ideas behind the potential ghost cavities in the paper, which Miriam had the link up a moment ago for it. Do we have any other questions? And if you have any questions for our first speaker, Meinik, please feel free to ask those as well.
I do have a question for our first speaker. There was a plot that you had shown that suggested, well, indicated that the large scale outflows had lower electron density compared to the small scale outflows, and you interpreted it as if the system had already excavated and had grown larger.
Yes, I think, let's say this one.
Yeah, that one. Yeah. I wanted to turn it around and ask, is there a difference in the environment? Right. I mean, we've been studying a type 1 AGN, a rare example of a type 1 AGN in a BCG. It's IRAS 09. I know it best as CL0910 plus 41. So it's also known as IRAS 0910 plus 41 at redshift 0.4. And it's been observed to have 1,000 kilometers per second outflow. How far out it goes, we actually haven't been able to figure out, because when we tried to do a IFU study, we couldn't find a bright star nearby to lock in on. But the question I have is that, could this be an environmental effect rather than an after effect of the outflow itself?
So we haven't actually been we haven't seen the large scale information, because like basically we are focused on the very bright part of the outflows. So unfortunately, we don't have the environment information, which is supposed to be done by another student. So yeah, I may not give you the actual exact information about the environment, but as far as I know, for the luminosity side or the black hole mass side, they are like very same. So on the AGN side, there is no difference, but there could be, as you said, that there could be like more gas, which might also could cause the high electron density in like certain outflows, maybe less gas and like lower electron density. No, we actually haven't we haven't seen anything super suspicious so far.
So it is worth looking to see what kind of systems these are in. If the host galaxy, for example, is an elliptical galaxy preferentially on one side, and the other one is a spiral galaxy, one could conjecture that maybe the CGM that would act as a resistance to the outflow.
Yes, I agree.
Is higher in an elliptical galaxy, and therefore confining it more.
Yes.
Anyways, I really enjoyed both talks, and thank you very much.
Thank you very much for the questions. I just wanted to thank our speakers once again very much for giving this talk. It was very wonderful. I'm sorry, Miriam, I'm going to embarrass you for a moment. I don't know for Meinik, but I know this was Miriam's first presentation, scientific presentation in English. I think she obviously did a wonderful job, and everyone would agree with me on that. So thank you very much again, Miriam, and thank you very much, Meinik. And that is it for me. Dennis, I don't know if you have anything else you would like to say.
No, I would just like to thank Carter again for taking on the effort of organizing these talks by graduate students. I would think it's a wonderful opportunity to have the community be aware of some of the excellent work being undertaken by our graduate students, and I think they add a lot to this Canvas platform. So hopefully this will be a monthly exercise where we have graduate students speaking, and there will not be a talk on Monday because it's a holiday for, I think, first Monday in August is a holiday. So we will resume again on August 10th. Just to let you know, since I work for the federal government, it's not a holiday for me. It's only so, but for everybody that works for universities and such, it is. So anyways, have a good week, everyone. And we'll see you in the Canvas talk on August 10th. Bye.
Thank you.